previous modules, we were talking about solution of hydrogen atom. Solution of hydrogen atom is a problem which is a real problem, and you saw in the previous module that we applied Schrodinger wave equation of in spherical polar coordinates, and in a spherical polar coordinates we have three different variables r, theta and phi. So what we did is that we separated the Schrodinger wave equation of spherical polar coordinates into three independent equations, each depending on only one variable. Okay. So we in the previous module we talked about solution of hydrogen atom. We were talking about solution of hydrogen atom. And in the previous module, we did the separation of variables of the Schrodinger wave equations of hydrogen atom in spherical polar coordinates, and we got three independent equations, each depending on only one variable. We got phi equation, we got theta equation, and we got r equation. Phi equation was very simple. Theta equation was also something which you earlier did in rigid rotor problem. So that was easy, and the solution was already known to you. So we got the solution of phi equation, we got the solution of theta equations, and then we combined phi functions and theta functions in order to get the spherical harmonics. And I said you that these spherical harmonics is actually the part of the wave function which tells you that how does the wave function varies with angle theta and phi angle. Okay. So that was angular part of the wave functions. Now we are concerned with the radial part of the wave functions, because r equations of the solution of the r equations we are going to do. Okay. So theta equations, if you remember previously, what you got was three independent equations, and out of that one of the solution was r equation, which is on the top of this slide. Okay. So this is your r equations which you are supposed to solve and get, and what to do, you should get a function which is r dependent, radial dependent. Capital R is the function and a small r is the variable I said you. Okay. In this equation Z is mentioned, so Z you can take equal to 1 because it is a hydrogen atom. Okay. And then this alpha which is in the red was actually beta in the case of rigid rotor, and this beta we found to be equal to L into L plus 1. So soon we will replace this alpha by L into L plus 1. Here I have replaced L into L plus 1 in the equation number 1 at the bottom. Okay. So the second equation which is written is nothing but multiplication of this function 8 pi square mu h square, and again see here mu we have used. I said you in case of rigid rotor that if you have a diatomic molecule rotating in a plane, then you can convert this two body problem into one body problem, and you instead of mass m you take mu reduced mass, and then it becomes a one body moving in a plane. Okay. And then we solve the theta equations and phi equations. That's already in the previous module, you can go and see. Okay. So here what I did is that I just multiplied 8 pi square mu with E and 8 pi square mu with E square by R. So 8 pi square mu by H square E square by R into RR. Now I have taken 8 pi square mu E square by RH square as 2 lambda alpha divided by R. This alpha and this alpha is different, so I have replaced it with L into L plus 1. Okay. And then we are then what you can say, if it is so, if you suppose this, if you suppose this, then alpha lambda becomes 4 pi square mu E square divided by H square alpha. Okay. So what is the value of lambda? You can see from here. So the first thing is that you let 8 pi square mu E square by RH square is equal to 2 lambda alpha divided by R. Okay. And where where this alpha will be, alpha square will be minus 8 pi square mu E divided by H square. So it's the same thing, alpha square. Then from the solution of theta equations we get this alpha which is in the red, L into L plus 1. So what you can do, you can you don't write where you suppose this also. Okay. Then it is easier. minus 8 pi square mu e square by h, mu e by h square is equal to alpha square. So now you have 1 by r square del by del r square del r by del r, no issue. Then you have 8 pi square mu e by h square. So this is coming from here, blue from blue, okay, minus alpha square, and then you have 8 pi square mu e square r h square, which is red, 2 lambda alpha divided by r, 2 lambda alpha divided by r, okay. So this is color coded, so you should not have any issue. This is alpha square, this is 2 lambda alpha r, so you replace these one. And then this alpha, the first alpha, which I said you was beta and theta equation, is L into L plus 1. So it is L into L plus 1. Now this is called, this equation number 1 can be rearranged slightly to give you 1 by r square del by del r square del r, this part, first part remains same, then minus alpha square plus 2 lambda alpha divided by r, and minus L into L plus 1 divided by r square multiplied by r. So from this second term and the third term, r is common, so we have combined these two, and the equation number 1 is this one, okay. So the solution is a little lengthy for the r equations, so you will have to see it patiently. But before you go for these slides, I said you earlier also, you must have a pen or paper with you and you start doing it yourself. Look at the slides and then start writing and start doing the solution, each equations you write, and then you will understand that how does one equation gets converted into another equation, okay. So if we move ahead and I go for this one, this was your slide equation, 1 by r square 2r d r by dr, r square d square r by dr, plus minus alpha square 2 lambda alpha divided by r, minus L into L plus 1 divided by r square into r is equal to 0. You need a solution for this to get RR, function RR, okay. This is a difficult solution, this is difficult to do, and so again what we do, we use the same technique which we used in power series method of simple harmonic oscillator and power series method of theta equations. So what we do is that we separate the, we change the variables, and we suppose a new variable rho is equal to 2 alpha r. So if alpha will become rho divided by 2r, and alpha square will become rho square divided by 4r square. So r we can write as rho divided by 2 alpha. You see, rho divided by 2 alpha. So 1 by r will be 2 alpha divided by rho, and 1 by r square will be 4 alpha square by rho. So you have 1 by r here. In this equation you have 1 by r. In this equation you have 1 by r square. So you can replace it with this one, and r also you can replace, okay. So this is, and if you differentiate this new variable rho, d rho by dr, then what do you get? You get 2 alpha. So dr divided by d rho you can write as 1 over 2 alpha, and so that dr is equal to d rho divided by 2 alpha. No issue, we can do this one. Now we change the variables. Since we have changed the variable rho, so instead of writing the function r, we will write s. So the function r was dependent on r, and now the new function s is a function which is dependent on rho, okay. So we will replace rr with s rho, and if we have to replace this one, then drr by d rho we can write as ds divided by d rho and d rho divided by dr, because this will go and you will have ds divided by d rho. So d square rr by dr square, again you can write d by d rho, drr divided by dr, d rho divided by dr, and then you get this one, okay. So you will replace both these differential, first differential and second differential, in the equation number 1 by this form, first differential, and by this form, the second differential, and rest of the values also you will put, you will see. We have a 1 by r is equal to 2 alpha divided by rho on the previous slide, and 1 by r square is equal to 4 alpha square divided by rho square, and drr by dr is this one, and d square rr is this one. So you replace these into the first equation. So what do? You have 1 by r square, so take one of the r inside the bracket, so this r will go and you will have 2 only. Then drr by dr, you have ds divided by d rho and d rho divided by dr in the blue color, so blue color is replaced, drr we have replaced. Then since one of the r is inside, so a square will go, and but r will remain same, r will remain there, and then double differential d square r by dr will be replaced by green equation d rho ds by d rho by dr and d rho by dr. Okay. So, this replacement is done. Then plus minus alpha square plus 2 lambda alpha into 1 by r. 1 by r was 2 alpha divided by r. So, 2 alpha divided by rho. So, 2 alpha divided by rho. Then 1 by r square is 4 alpha square divided by rho. So, L into L plus 1, 4 alpha square divided by rho, and again RR is replaced by S rho. Okay. So, you get this equation. Now, the variable is changed, the function is changed. The variable is rho now and the function is S now. Okay. So, d rho by dr we got as 2 alpha. Okay. So, what do we get? Now we have 1 by r 2 ds divided by d rho. This is the same equation, minus alpha square 2 alpha divided by rho, same equation as we got it. Okay. Now, what I did, what we have taken, this first part of the equation, that is 1 by r 2 ds divided by d rho and d rho divided by dr, plus r d by d rho, ds divided by d rho by dr, d rho by dr, this remains same. This part no changes. But here you have 2 into 2, 4, alpha into alpha is equal to square. So, 4 alpha square you have here, 4 alpha square you have here, and here you have alpha square. So, out of the second term, 4 alpha square is taken as common. If you take 4 alpha square common, then the first term will be minus 1 by 4. First term is minus 1 by 4. Then the second term is alpha divided by rho, because 4 alpha square we have taken common, and this 4 alpha square is gone. So, L into L plus 1 divided by rho square into S rho. So, the only change from the first equation to the second equation on this slide is that 4 alpha square has been taken common from the second equation. Okay. Once you have done this one, then what you can do is, since d rho divided by dr is 2 alpha, so d rho divided by dr you have here. Okay. So, what you can do, you can ds divided by d rho and you can put 2 alpha, then r d by d rho and ds divided by d rho and d rho divided by dr, again rho divided by 4 alpha square. Okay. So, you have d rho divided by dr and d rho divided by dr, so it is 4 alpha square, and you have this multiplied by this will be d square s d rho square. So, I put this as d square s by d rho square. Okay. And then r is equal to what? Just I should have written here also. Your r is equal to rho divided by 2 alpha. Okay. So, r is equal to rho divided by 2 alpha. Oh, sorry, 2 alpha. Okay. So, this r is rho divided by 2 alpha. Okay. And 1 by r is equal to 2 alpha divided by rho, this you know. So, 1 by r is replaced by 2 alpha divided by rho. Then you have d rho divided by dr is equal to 2 alpha. So, it is 2 alpha here. This also should have been blue. Okay. 2 alpha. So, this is d rho divided by dr. Then d square s by d rho square, fine, and d rho divided by dr is multiplied by this d rho divided by dr. So, you have 2 alpha and 2 alpha multiplied by 4 alpha square. Okay. So, this part is now fine with the previous equation, and if you multiply by 2 alpha by rho within this bracket, this part remains same, 4 alpha square. The second equation is no change. Okay. The second part of the equation is no change. In the first part, if you multiply by 2 alpha divided by rho, what happens? This alpha divided by rho, 2 alpha and 2 alpha divided by rho goes, and what you have, if you have multiplied by this one, so 2 alpha into 2 alpha divided by rho and 4 alpha square. So, you have 4 alpha square here also and 4 alpha square here also. So, this 4 alpha square you can bring outside. One of the 4 alpha square is this one, another 4 alpha square is this one. Okay. So, you can bring it outside, and now you have 2 divided by rho, ds divided by d rho plus d square s divided by d rho square. plus 4 alpha square, and this part remains same, minus 1 by 4 plus lambda divided by rho minus L into L plus 1 divided by rho square into S rho is equal to 0. Okay. So, remember that we have changed the variables and we have changed the representation of the function also. From capital R, now it is capital S, okay, which is dependent on rho. So, a little rearrangement, now 4 alpha square you have in the second term also, you have 4 alpha square in the second term, first term also. So, take 1 4 alpha square and as common and then combine the whole equation. So, 2 divided by rho ds divided by d rho, 4 alpha square is now common. So, 2 divided by rho ds divided by d rho plus d square s divided by d rho square plus minus 1 by 4 plus lambda divided by rho minus L into L plus 1 by rho square into S rho is equal to 0. Okay. So, what does this equation tells you? This equation tells you that the portion within the bracket can be taken as 0. This you can take as equal to 0 because this whole equation is 0. So, you write d square s by d rho square plus 2 divided by rho into ds by d rho, and then the next equation is alpha divided by rho minus 1 by 4 minus L into L plus 1 divided by rho square. So, we can write it like this one with a little changes from position from one place to another place. So, you write it like this one, this equation we got. Okay. Now, this equation is not easy to solve. An asymptotic solution can be guessed for a very high value of rho. So, if you take a very large value of rho, what will happen? For very large value of rho, since they had rho is in denominator, in the second part, 2 divided by rho ds divided by d rho, then lambda divided by rho, so again rho is in the denominator, L into L plus 1 divided by rho square, so again rho is in the denominator. So, for a very large value of rho, you can neglect all these parts, because here you have all these parts you have rho in the denominator, and if you neglect all these parts, then what remains? The only term remains is d square s by d rho square, second differential, plus then plus minus and s divided by 4, because L into L plus 1 divided by rho square can be neglected, lambda divided by rho can be neglected, and 2 by rho ds by d rho also can be neglected. So, what the solution, the equation remains for an asymptotic behavior for very large values of rho is d square s by d rho square minus s divided by 4 is equal to 0. And this again is a very simple equation, and you are aware of this solution. You are aware of d square psi by dx square plus k square x is equal to 0. What is the solution? Okay, so that solution you know. Okay. So, an asymptotic solution we are writing, and we are writing it for the s variable, s function, rho is the variable. Okay. So, this gives two different solutions. One is s is equal to exponential rho divided by 2, and another is s is equal to exponential minus rho divided by 2. So, this equation number 2 we got from equation number 1, the original equation of the hydrogen atom, or equation of the hydrogen atom. So, any solution of the first equation will have a term like this one, exponential minus rho divided by 2, okay, because it is coming from that solution, and it is a special case, an asymptotic solution we are talking about, where the rho value is extremely large. So, we have neglected other parts of the equation. So, and now out of these two solutions, obviously you know that the function should not be infinite. So, the solution which is acceptable is exponential minus rho divided by 2, an acceptable solution. S is equal to exponential rho divided by 2 is not acceptable, minus rho divided by 2 is an acceptable solution. So, any solution of the hydrogen atom or the R equation, first R equation, should have or must have this particular term, similar to this term, exponential minus rho divided by 2. Okay, this exponential term should be there. Now, if you got this solution, an asymptotic solution, then what we say that if this is not the total solution, this is an asymptotic solution. So, the solution of equation number 2, which we are doing here, solution of equation number 2, we have omitted many terms, 2 divided by rho ds by d rho, lambda divided by rho, and L into L plus 1 divided by rho square. So, any solution of equation number 2 will have this exponential minus rho divided by 2 plus some additional term should be there, because the neglected terms that will account for all the neglected terms. So, we say that the solution has another term f rho, an additional term. So, the solution of equation number 2 is f rho into exponential minus rho divided by 2. This is this part of the solution, exponential minus rho divided by 2, we got from asymptotic solutions, and this we are adding because many 3 terms of the equation number 2 we neglected as an asymptotic behavior for a very large value of rho. So, we add a new term f rho. If it is so, if we suppose this to be a solution of equation number 2, then what we can do? We can differentiate this equation ds rho divided by d rho, and if you differentiate, you have 2 terms. First term is f rho and second term is exponential minus rho divided by 2. So, you keep the second term constant, differentiate the first one, then you keep the first term constant and differentiate the second one. You get this equation. Okay. Then do the second differentiation, and in second differentiation you have again 2 terms here and 2 terms here. So, the second differentiation will give you exponential minus rho divided by 2 keeping constant, and the second differential of f rho. So, d square f rho divided by d rho square minus again differentiation of exponential term and keeping the df rho divided by d rho constant will give you this term. Then again keeping the differentiation, keeping the exponential minus rho divided by 2 is equal to constant and differentiating df rho, and then keeping f rho constant and differentiating this term, first term will give you this one. So, we have the d square s rho divided by d rho square, we have ds rho divided by d rho square. So, we can substitute these values into equation number 2, from which we got the asymptotic solution exponential minus rho divided by 2. So, if you substitute this equation, what do you get? You get this one. You see, the first part of the equation number 2 was the d square s rho divided by d rho square. So, that part is in the red, which we have written here. Okay. Then you have 2 divided by rho and ds rho divided by d rho. So, ds rho divided by d rho is this blue part, exponential minus rho divided by 2, df rho divided by d rho minus 2 exponential minus 2 divided by rho exponential minus rho divided by 2 into 2 f rho. Okay. So, this is your d square s divided by d rho square, this is your ds divided by d rho. Okay. First differential and second differential. Rest of the equation is same. The third term lambda divided by rho minus 1 by 4 minus ln 12 plus 1 divided by rho square, and here you were having s rho. So, instead of s rho, now you write the first equation f rho divided by exponential minus rho divided by 2. So, your equation number 2 now changes to this equation. Equation number 2 is now this one. Okay. Substituting these values in equation number 2, you get this one. And what you do with this equation? You rearrange this equation. So, this is the same equation, exponential minus rho divided by 2 you take common, and you have d square f rho divided by d rho square minus df rho divided by d rho into 1 by 2. This has gone outside. Then minus 1 by 2 df rho divided by d rho, then plus 1 by 4 f rho, okay, plus 2 by rho df rho divided by d rho. Okay. Then you have minus 2 by rho 1 by 2 f rho, okay, and then plus lambda divided by rho minus 1 by 4 minus lambda L into L plus 1 divided by rho square into f rho. So, this remains same. Okay. So, from here, from this part we take exponential minus rho divided by 2 as a constant, as a common factor, and you get this equation. Okay. You rearrange this equation, you have exponential minus rho divided by 2 here also, and you have exponential minus 2 rho divided by 2 here also. So, why not combine all these equations? So, combine everything, and then you have d square f rho divided by d rho square plus d f rho divided by d rho, and then you have taken common df rho you have here also, df rho you have here also, df rho you have here also. Okay. So, take the common of these, and then you have minus 1 by 2 minus 1 by 2 plus 2 divided by rho, minus 1 by 2 minus 1 by 2 plus 2 divided by rho. Okay. And then you have f rho divided by 4 and plus f rho divided by 4 it comes from here, and minus f rho divided by 4 comes from here. Okay. So, you have this one, and which will go, because you have f rho divided by 4 and minus f rho divided by 4 plus lambda f rho divided by rho, lambda f rho divided by rho minus f rho divided by 4 and then minus f rho L into L plus 1. Okay. So, this I think this I have already taken f rho. This is an extra term, I think. Okay. It should not be here because minus f rho divided by rho I have written here. Okay. So, what do you get? You get d square f rho divided by d rho square plus d f rho, and now minus will be 1. So, 2 divided by rho minus 1, and then you have lambda divided by rho, lambda into lambda minus lambda into lambda plus divided by rho square into 1 by rho f rho divided by so you have this, up to this it's fine, and this should be f rho divided by 4 lambda f rho divided by 4 f rho into L plus 1. Okay, fine, that's fine. And from where you get this one, 2 divided by rho is up to this one. Okay. So, this was your f rho divided by 4. No. So, this was your f rho divided by 4. This will remain. Okay, fine. Okay. This will remain there. Okay. So, now you have 1 over rho. Now, this is your equation number 3. Hence, the problem has been reduced to the determination of f rho. And now, you see, you started with d square RR by dr square. Then you change it to d square SR by d rho square. Now, we have changed it to d square f rho divided by d rho square. The boundary condition of this equation is that your function RR should be 0 at R is equal to 0. The singularity at the origin prevents the particle from being found at R is equal to 0. We are finding out the electronic wave functions. So, electron is present outside the nucleus, and so the singularity is that RR should be 0 at R is equal to 0. And another is that it should not be, it should be 0 even at infinity. The function should be 0 at infinity also. So, the second boundary condition ensures the square integrability character of the wave functions. And if you use this singularity, then a solution of this equation could be written as in a power series. So, this is a non-vanishing constant term rho raised to the power s, and this is a power series L. So, if you write L in terms of rho, a power series, then what you can write? You can write L is equal to A0, A1 rho, A2 rho square, A3 rho cube, A4 rho cube, and so on. So, you can write this power series. Okay. Now, if you differentiate this one, d f rho divided by d rho, then what do you get? You differentiate keeping rho raised to the power s constant, and then differentiating L dl divided by d rho. Then keep L constant and differentiate this. This will be what? S rho raised to the power s minus 1, S rho raised to the power s minus 1. So, f you can differentiate. Now, you can double differentiate also, because in the previous equation you have double. So, you are going to do the same thing which you did earlier for s. Now, you are doing it for f. So, d square f rho divided by d rho square will be what? Keep this term constant, double differentiate d square L by d rho square, then keep dl by d rho constant and differentiate this one rho raised to the power s. So, it will be s rho s minus 1. Then again keep this second term constant s rho s minus 1 and differentiate dl divided by d rho. Then keep L constant and differentiate s rho s minus 1. So, it will be s minus 1 rho s minus 2. Okay. So, the second differential is this one. Second differential d square f rho divided by d rho square is equal to this one, a little rearrangement. So, you have the f rho function, you have the first differential function, you have the third differential function. You can put these values again back into the equation as you did earlier in equation number 3. So, okay. So what you get? If you put these equations, ds rho square, and before that you have this equation number 3. So, multiply this equation by rho square. Multiply this equation by rho square. So, rho square you multiplied, rho square you multiplied, rho square you multiplied. And what do you get? rho square d square f rho divided by d rho. Then you have df rho divided by d rho, and rho square multiplication will give you 2 rho minus rho square, because this rho square multiplication will give you this one, and if you multiply with this one, you will have lambda rho into f rho minus L into L plus 1, this rho square will go f rho, and then minus rho f rho. Okay. So, it will be, you have multiplied the whole equation by rho square, so no issue, and then slight rearrangement rho square d square f rho divided by d rho square plus 2 rho minus rho square d f rho divided by d rho plus lambda minus 1 rho into f rho minus L into L plus 1 f rho, okay, is equal to 0. Okay. So, we got this and this we combined, nothing else. Okay. Rho f rho is here also, rho f rho is here also, so lambda minus 1. Okay. In this equation, you put all the values which we got for f rho in terms of previous equation. Here, f rho is equal to rho raised to the power s L to L, and d f rho divided by d rho is equal to this one, and d square f rho divided by d rho square. So, if you put these values in the modified equation number 3, then what do you get? Rho square d square f rho divided by d square is this one. All the terms is there in the previous slides, so you can go and check. Then you can write 2 rho. So, rho square is equal to this one. Then 2 rho multiplied by this equation d f rho divided by d rho, and minus rho square also multiplied by d f rho divided by d rho. It is the same term here also and here also, because in the both cases you have df divided by d rho. So, df divided by d rho term is at 2 different places, and then f rho is also at 2 places. F rho is this one, rho raised to the power s into L and rho raised to the power s into L. So, this equation number 3, which is modified by multiplying with rho square, is now the last equation on this slide. Okay. So, what else we can do? We can again look at this slide, and if you rearrange this slide again and combine the different terms, what you can write is this equation. So, you see rho into s plus 2 d square L by d rho square. The first term, I will not go for every term, you go and see, and finally what you get is you look at this term, the first term. So, it is rho s plus 2 d square L by d rho square. Then again 2s rho s plus 1, because you are multiplying with rho square. So, it will be rho raised to the power 2 plus s minus 1, and it will become rho s plus 1. Okay. So, it's simple multiplication gives you this one, and if you rearrange, you get this equation number 4. This equation is an entity in rho, and therefore, the coefficients of individual power of rho gets vanished. Okay. So, this equation we say equation number 4 we got. Okay. And the solution for this equation number 4 we will see in the next class, because it is a very lengthy calculations. So, we must take a break, and after taking the break again I will start from this equation number 4 in the next module. Okay. Thank you.